When observing the cosmic microwave background at its largest scales, where multipoles fall below 30, we find persistent structural deviations. These scales exhibit four distinct anomalies: a deficit in large-angle power, an anomalously low quadrupole, an odd over even parity asymmetry, and a quadrupole-octopole alignment. Individually, these features are statistically modest, sitting at a 2 to 3 sigma level of significance. Yet they've consistently survived adjustments to statistical estimators and masking techniques across 3 generations of satellite missions: COBE, WEMAP, and Planck. The scientific weight of these anomalies does not come from any single feature acting as decisive proof of new physics. The weight comes from their shared presence at the exact same vast scales, pointing to an issue within a common physical sector. Together, they establish a durable empirical tension within the standard lambda CDM model. Resolving this tension requires a unified geometric framework, which brings us to the primary candidate, cosmic topology. The topological hypothesis proposes mapping the observable universe onto a compact quotient space, giving the cosmos a complex, closed shape to explain these large-scale deviations. The mathematical subject of this specific analysis is the Poincare homology sphere, defined formally as the manifold S3/2I. To successfully deconstruct the four anomalies, we have to strictly separate the intrinsic mathematical properties of this specific manifold from our physical cosmology. Our analysis relies on 2 fixed facts about S3/2I that hold entirely independent of cosmology: its strict chirality and its rigid scalar spectrum. These mathematical traits will sort the anomalies, while the physical curvature radius, r, will dictate how they project onto the sky. Validating this framework means proving that the spatial topology natively generates the missing power entirely on its own, without relying on circular curve fitting. We begin with the first 2 features: the parity asymmetry, where odd multiple power exceeds even power, and the quadrupole-octopole alignment. The initial question is whether the inherent spatial geometry of S3/2I can naturally grade even and odd multiples to produce these specific features. This requires looking at quaternion isometries in an S3 space. Every orientation reversing map takes the algebraic form Q maps to U times bar Q times V. On this manifold, the binary icosahedral group, the 2I and S3/2I, acts strictly by left multiplication. Applying any orientation reversing map forces that left action to become a right action. For non-central elements, a left translation remains distinct from a right translation, resulting in a strict geometric mismatch. The resulting mathematical theorem is absolute. The manifold S3/2I is strictly chiral. It admits 0 orientation reversing self-isometries. This absolute chirality directly shuts down earlier cosmological models that attempted to explain the parity anomaly by enforcing orientation reversing Mobius boundary conditions. Parity and alignment anomalies cannot emerge as structural artifacts of the S3/2I topology. They remain open problems driven by the anisotropic covariance of the manifold's eigenmodes, effectively moving them off the purely topological ledger. This shifts our focus to the remaining 2 empirical features: the large angle power deficit and the anomalously low quadrupole. On a standard unconstrained S3 manifold, scalar harmonics are continuously graded by their polynomial degree, n. The quotient space S3/2I imposes a strict restriction. Only the 2I invariant harmonics survive. The space's center acts on degree n by alternating signs, completely knocking out the odd degrees and limiting the surviving harmonics to even numbers of n. We calculate the surviving invariance using the Molien series of the invariant ring. This equation contains specific generators at degrees 12, 20, and 30, corresponding to the 3 Klein icosahedral invariants. The rigid mathematical consequence of this series is that the shells for n equals 2, 4, 6, 8, and 10 are completely empty. The very first non-trivial invariant appears solidly at n equals 12. This void is the Molien shell gap. This structure is topological, fixed by the mathematics, and operates entirely independent of any physical cosmology. This topological shell gap provides the intrinsic, unalterable structural mechanism for the missing large-angle power observed in the cosmic microwave background. The topology guarantees the gap exists, but what dictates where that power drop-off lands on the observed sky? This chart maps observable multipoles against power, showing where the theoretical harmonic shells translate to our sky. The translation is governed by a characteristic multipole equation, which relies on the physical curvature radius, r. The cutoff boundary, set by the last empty shell at n equals ken, scales inversely with the curvature radius. As the numerical value of r increases, the cutoff drops to lower multipoles. Historically, this caused a significant coordinate error in the field. This imposes a strict methodological rule. You cannot read r backwards from the CMB deficit itself to make the math fit. That is circular curve fitting. To prove the topology is genuinely responsible for the deficit, the curvature radius must be derived from independent non-CMB routes, and that independently derived number must project the shell gap directly into the observed band. The framework utilizes two entirely independent physical routes to calculate the precise scale of r. The first calculation is the coupling route. This derives the radius by fixing the cosmological constant to roughly 24%, yielding an r of approximately 5.3 gigaparsecs. Looking back at our multipole projection chart, an r of 5.3 gigaparsecs drops the last empty shells squarely near an L of 28. This perfectly aligns the theoretical gap zone with the actual deficit band we observe in the sky. The second calculation is the mass spectrum route, which provides an order of magnitude reading pointing to an r of roughly 20 gigaparsecs. Projecting this onto our chart, an r of 20 gigaparsecs shifts the cutoff drastically downward to an L of 8. This creates a massive physical mismatch, failing to cover the observed deficit band. This leaves us with a stark split. The well-conditioned coupling calculation hits the target perfectly, while the rough mass spectrum calculation misses entirely. Resolving this specific numerical discrepancy remains the ultimate open problem. The validity of the entire structural framework hangs on unifying these two independent readings of the curvature radius. The S3 over 2I framework forces a rigid mathematical accounting of the cosmos, strictly separating the pure topology of the manifold from the physical scale of the universe. While previous observational nulls, like Planck's search for matched circles, placed constraints on standard FLRW models, those tests analyzed entirely different fundamental domains. In this specific geometric framework, those results act as a consistency check rather than an exclusion. The true test of this model is its absolute, unforgiving falsifiability regarding the curvature scale. The topological void is an unchangeable fact of the math, but the physical footprint of that deficit is dictated entirely by r. If the final, independently verified curvature radius places the cutoff outside the bounds of the observed deficit band, the geometric explanation fails outright, and the topological hypothesis of S3/2I is definitively falsified.